Okay, so today we start on measurable functions, one of the most fundamental objects in this course. See, lot of times in analysis, this thing is there, the parallel between sets and functions. So lots of things are like that. So you have some statements about sets, and you have some analogous statements about functions. Okay, so in some sense, so many things we can formulate either for sets or for functions or for both. And there may be a little bit of difference in the two, I mean superficially. So, yes.
Your screen is not shared.
Screen is not shared? No, I thought I had shared it.
It's fine for me.
No, sir, it's
I can see that.
Oh, okay.
So,
Then
someone not see it? Is it still not visible? Is there anyone to whom it is not visible? Chinmay, right? Who asked?
It's not visible to me as well.
Not visible. Okay, let me.
Actually, I rejoined and then I can see it. Previously, I was not able to see it, so I think anyone can rejoin. Then.
Yes, same.
People can try just rejoining. I'll give a minute. So, did people come back? Can you see now, everyone?
Yes.
Is there anybody who cannot? Chinmay, can you see it now?
Yes, yes.
Yes, okay. All right, in that case, I'll start. So, let's just check the recording. Is it on? Okay, recording is on. Okay. So, many things about sets and functions. So, in that sense, okay, I will not explain that statement now, but it will be illustrated many times over in analysis. So, what measurable functions are, just like measurable sets. Okay, measurable sets are finally if we just stick to R, which is kind of a basic case, R or RD. Finally, measurable sets were the ones to which you could associate length, area, volume. That's what they were in the end. Okay, so the technical definition may look more complicated. It may come from Carathéodory condition or some other criteria. That's not a problem. But ultimately, what they were sets. Those were the sets for which we could talk about length, area, volume, and so on. Now, measurable functions are exactly going to be similar things. They are the functions to which we are going to be able to talk about integrals. Okay, so that's what essentially it is. Okay, it's a bit more general than that, but that's how you think of it. So these are functions for which you can think of integration. Okay. So, and sets will be a special case of functions. Quite often that is the case. I mean, okay, I'll explain that later. But let me recap the definition which I already have given. But let's go over it because now we will start afresh. Okay. So, what is it? So, remember we have two measurable spaces, XF and YG are measurable spaces. Measure is not necessary yet. On neither of them we need to have any measure. So a function from t from x to y is said to be measurable if t inverse of b belongs to f for all b belongs to g. Okay, so and let's some point I have made before, but worth telling again because mistake on this would be very bad. So you cannot afford to make this mistake. T inverse b, there is no function called T inverse here. If there is an inverse for T, we will also call it T inverse. But T inverse B is one unit. Okay, so T inverse B is the inverse image of B. So this is called inverse image of B. Under T. So B is any subset of the domain codomain Y. Okay, so T inverse B is all those X in X such that when T is applied to that, it will fall into B. Okay, so X is here, Y is here, and if you take a subset B, all those things that get mapped into, you collect them together. That is T inverse B. So that's what it is. It's the inverse image of B. So forward image also makes sense. T of A is, so forward image would be, well, you don't need it now, I'll tell it later. So that's what definition of measurability is. So this is of course with respect to the sigma algebras. But quite often we are clear about which sigma algebras we are talking about. So with respect to F and G, okay, it's with respect to those sigma algebras that the definition is made. Okay, so that's the definition. So we'll come to examples. First, let me talk a little bit in generalities and then give examples. There are lots of examples. In fact, the situation is going to be just like with sets. It will be difficult to give a function which is not measurable. Just like it was not so easy to give a set that was not measurable, it will be difficult to give a set. Okay, with my choice of sigma algebras I can give, but with the usual sigma algebras it will be hard to find something that's not measurable. Most functions that we are interested in will be measurable. Okay, so but before coming to that, so let's say one thing. So let's make a couple of remarks. So let's understand some generalities of this. Okay. So one thing to notice is that so suppose T is, so F is, whether or not F is given. Okay. So here, so just to be clear, let's say T is from X to Y, and I have given the sigma algebra here. Maybe I have not given it here. Okay. So the set of all B such that is a sigma algebra. Okay. So there are a couple of exercises or something that I wrote last time. So you should do it yourself. So when we take inverse image, goes well under set operations like this. B complement, the inverse image will be T inverse B complement. Also, T inverse of a union of sets. This is not even a countable one. Okay, this is even true without countable. So countability doesn't come here. So this is true for arbitrary unions. So T inverse of the union BI is T inverse BI union. Okay, so this is important. Forward, so this is completely fails for forward images, by the way. So it is something that you should keep in mind. Fails. Okay, so T of A, if I take A contained in X, T of A complement is not equal to T of A complement. Okay, in general, that's not true. Imagine a constant function. So imagine a constant function where everything is getting mapped to one particular point, let us say. Okay, everything gets mapped to this point. So then T of any set is actually that singleton. Any non-empty set, T of that is the forward image will be the singleton. So this is certainly not true. T of A complement won't be T of A complement. Okay, so this is very important to keep in mind. Inverse images are good, but forward images fail. Anyway, If you look at all those B in Y such that T inverse B belongs to F, that is a sigma algebra. Hence, so is if I have a sigma algebra here, if I take all those B in G, so for the moment, if I call this G hat, so all those B in G such that T inverse B belong to F. This is nothing but G hat intersection G. Is also a sigma algebra. Okay, all those sets here in G, whether you start with G or whether you start with all sets, those sets for which the inverse image belongs to F, that's a sigma algebra. This is actually a useful point. Why do I bother to say it? It is useful because of the following thing. See, this business of checking measurability seems a bit complicated, right? Because the sigma algebras in most realistic situations, we don't know them explicitly. That's the point I have been hammering away many times. That you don't know the sets in the sigma algebra. So how am I going to check T inverse B belongs to F for all B in G? So I have to go over all sets in G. That seems a bit complicated. But because of what I have said here in red, as a corollary to that, it follows that if T inverse B, suppose I manage to check T inverse B belongs to F for all B in some S, okay, where S generates the sigma algebra G, then T is measurable. Okay, so in other words, you only need to check the condition for generating collection of sets on the right side. So you don't have to do it for T inverse B for all B in G directly. You only have to do for B in S, where S is something that generates the sigma algebra G. How does it follow from here? Well, it is kind of clear, right? So you look at this set B in G. This is a sigma algebra. So what is the reason for this corollary? This is a sigma algebra. And what you are saying is it contains. So this is a sigma algebra containing S. Assuming that this condition holds for S, for all B in S, this is a sigma algebra that contains S. Hence, contains the generated sigma algebra, which is G. But that means it is G because that's anyway a subset of G. So it would be G. So this reduces your checking. You don't have to do it for all sets. You only need to do it for these sets. Okay, so let's a particular example. In fact, most of the time when we talk about measurable functions, we are going to be talking about the following situation. Maybe I should explain that, or maybe yeah. So let me explain that here. So when the target space or maybe I stick to generalities first and then come to real numbers. Okay, so maybe just to not make it confusing. So let's make another remark and then go to real numbers. So another point is that suppose I have T from X to Y. This time I give the sigma algebra here, and then I look at the set of all T inverse B in G. So I take the inverse image of all sets in this sigma algebra. So this is itself a sigma algebra. Okay, both this point and this point I have left as assertions. I will leave it for you to check. It is a very simple exercise to check using these properties here that inverse images go well under unions and complements. Because of that, this follows. So I will just leave that. That's a trivial checking. So I will leave you. So this is denoted sigma of T. Okay. So why do we call it sigma of T or the sigma algebra generated by T? Okay, so why do we call it that? So that is, by the way, sigma algebra on X. This is a sigma algebra on this side. So sigma of t is here. It's a sigma algebra there. So it is the, what is its property? It is the smallest sigma algebra f on X such that t from X to Y, if I put f here and g here, is measurable. See, for t to be measurable, f should contain all these sets, t inverse b. So, but that collection itself is a sigma algebra. So, that is the smallest sigma algebra with respect to which t becomes measurable. So, that is called a sigma algebra generated by t. Okay. So, that's just a notation or a general notion which we have introduced. So, these are some remarks. And at the level of generalities, what do I want to say? So measurability is preserved under some things. So one of the things under which measurability is preserved is like this. Suppose I have x with f, y with g, and z with another set with sigma algebra f. And suppose I have a function t here, and suppose I have s here. If t and s are measurable, then so is the composition S compose T, which is a map, by the way, from X to Z with F here and H here. Okay, so this is the claim. So this is a very simple but very useful point to note. So one of the things, I mean, so what are we going to do? I have not given you examples of measurable functions. I will give examples. But one of the things, just like with the measurable sets, one of the ways we say that lot of things are measurable is that under lots of operations, measurable functions are going to remain measurable. You can take limits, you can do this, you can do that, etc. Right? We will remain within the measurable class. So this is one of the first properties I'm saying, that it is preserved under composition. Okay. So what is the proof? So just for clarity, let's give U as S compose T. This is from X to Z. So if you look at U inverse of some set C, let C be in H. Okay, so what is U inverse of C? I say it is just T inverse of S inverse of C. Okay, see, these are the points such that if you apply U, you fall into C. U of X should be in C. So if U of X should be in C, then I mean this point is S of T of X belongs to C, means T of X belongs to the inverse image of C under S. So what does that mean? X belongs to inverse image of this under T. That's what I have written there. Okay, so that's what I have written here. So, but now this belongs to G, and therefore, because C belongs to H and S is measurable. Now this is a set in G, therefore T inverse of that will belong to F, because T is measurable and S inverse of C belongs to G. Okay, so therefore U inverse C belongs to F for all C in H. So that is U is measurable. So compositions preserve measurability. So this is the thing. Any questions or any comments or anything? Okay. So most important for us, I mean, we will use measurable functions in general spaces also a little bit, but most important are measurable functions into the real life. So let's come to that. Most important cases. So we will do a little bit at this level of generality also. It is very useful notion, but most important thing is for us so when you have a function into real numbers, okay, and RD also, but let's just stick to real numbers for a moment. So many times when we just say measurable function, we mean real valued measurable functions, and then this is the thing. But what sigma algebra on R? Here it is extremely important, since we have spent a month doing this business. It is extremely important that here we always mean just the Borel sigma algebra, okay, not the Lebesgue sigma algebra. When I is a target space, this is all we want. Okay, so if you want to remember which way, you remember so that more things will be measurable. Meaning that if you make the sigma algebra here larger, that will put more restrictions for your functions to be measurable. We don't care for that. We only want the Borel sigma algebra here. Okay, so this, when this we say T is a real valued measurable function. Okay, so it's always meant that this side we will have the Borel sigma algebra on the real line. Okay, so this many books first define, or some books only just define measurable function to be into real numbers, but the general notion is useful, so I have just defined it. But most of the time, these are the ones we are going to use. For example, integration, etc., will be done for these types of functions, not into a general space. Okay, so how do we check this? Because of what we said, so what generates the Borel sigma algebra? BI is generated by, there are lots of collections which generate Borel sigma algebra, right? What are some examples that you can tell? Collection of sets which generate the Borel sigma algebra.
Left open, right closed intervals.
Okay, so for example, left open, right closed intervals. That is a small, we would like the collection to be small so that our checking is reduced. Okay, so even we can even take just minus infinity t. That we don't care for it to be an algebra, I mean, etc. So if we take minus infinity t, this generates the Borel sigma algebra. Okay, so does actually minus infinity open t, for example. Because it is quite clear, right? Any left open, right closed interval will be a difference of two of these things. And this is, if you have it for all open sets, you can write this as an intersection of countably many of these. So if you take minus infinity to t plus 1 over n open and the intersection over n, then you get minus infinity to t closed. So there are other collections also. I mean, you can take minus infinity to, t to infinity. Or you can take close t to infinity. All those will do. And so because of that, what is the point? Here I said that if you have on the target space, if G is being generated by a collection S, then it's enough to check T inverse B belongs to F for those sets in the generating collection. So what does this tell me? So if I use this, so T is measurable. So T is, by the way, T is a mapping from X with some sigma algebra F into real numbers. Okay, so T is a mapping from X into real numbers. T is measurable if and only if inverse images of these sets are measured in F. So what is the inverse image of this? What is T inverse of this? So I will write in the case, what is T inverse of minus infinity T? It means it is all those X in capital X such that T applied to X will fall inside that set, meaning less than equal to T. Again, T inverse of minus infinity T is just all those X such that Tx is less than equal to T, which is, we'll just write it as T less than equal to T. Okay, this is a notation we'll be using a lot, so I'm not sure whether anywhere else you had occasion to be using this kind of notation in any other course. So that's why let me explain, even if it is already familiar. So when we write something like this looks
It's
like,
4 o'clock.
what is this? You should read it out in detail as all those X for which T of X less than equal to T. So this is a short form, but extremely convenient for us to be using this short form rather than every time write X in capital X such that Tx less than equal to T. This is a short form, but you should get used to it and then be able to quickly say, where is this set? It is a subset of X. Okay, so that's what it is. Anyway, so with this notation, what is it that we are saying? That, so I will erase all this. Okay, so let me just write here. So that notation, let it stay there. So let's write here, T is measurable if and only if the set T less than equal to T is a measurable set for all T in real numbers. But you can also use any of these other generating sets. So you can also write if and only if. If I use this, what would I write? It is capital T less than T belongs to F for all T in R. Or if you use this collection, you will write it as T bigger than small t belongs to F for all T in R. And if you use this last one, okay, that is closed, right? So that is same as T greater than equal to small t belongs to F for all T in R. So you could use any of these things which seem more convenient. You don't have to worry about T inverse image of some Boyle set. You just have to check whether T less than T, T bigger than T, etc. are measurable. Is okay? Is there any question, comment, or anything on this? So to check measurability of a real valued function, you just have to check these things. So as a quick cover, for example, very quickly we can say, so just as since I didn't give example, suppose T is a function from R to R with both this being Boyle sigma algebra, this being Boyle sigma algebra. Okay. Suppose I take this. If T is increasing, then it is measurable. Okay, that's very easy. Why? I mean, because you look at so from these criteria, it is very trivial. I mean, you don't have to. Increasing means I actually here meant non-decreasing. So why is that? Because the reason is very simple. Because if you look at something like T less than equal to small t, is of the form, is an interval of the form minus infinity to x, or it could also be minus infinity to little x, or it could be, of course, empty set is possible, or minus infinity to infinity is also possible. I mean, it is one of these, right? Because it's an increasing function, imagine. So it is an increasing function. That doesn't look increasing. Sorry. Let me draw a picture here. So you have an increasing function. It can stay constant for a while. It can also jump. It can jump and do all sorts of things. But if I look at the inverse image, so here is, so this is the graph of the function I have drawn. Now if I take a t and look at set of x for which tx is less than equal to t. Suppose that line is like this. And I am looking at x for which tx less than equal to t. That means it will be everything up to here. So if this is t, then this will be t less than equal to t. So it's always some sort of an interval, hence measurable. Hence Boyle. That's what I want to say. Because I put B here, hence Boyle. Okay, so is it clear? So that is increasing functions, for example. Now you have lots of examples of measurable functions. So I didn't say they have to be continuous or anything. It can have jumps, it can stay constant, it's not strictly increasing, etc. So another thing, T from R to R. Yes, question?
Sir, I think sometimes back you made an argument where I lost you. You said that okay, it's enough to check on
the sentence again from the beginning.
Yeah. So you mentioned sometimes back that it's just enough to check on some collection, smaller collection S, and then you can say that okay, it's measurable. Can you just repeat that argument?
Which one here? Okay. So yeah. So let us look at. So what I said was, you look at the set of. So you want to say, suppose it is true that T inverse B belongs to F for all B in S, where S generates the sigma algebra G. Okay. So now what I do is, so you forget all this. You just look at all those B in G such that T inverse B belongs to F. Let's look at it's. You look at this collection. As usual in measure theory, you want to prove some collection is something. You consider all sets with that property. Okay. So look at all sets B in G for which T inverse B belongs to F. What you have been told is this collection contains S. And then I have asked you to check that that is actually a sigma algebra. So it's a sigma algebra that contains S, so it contains G. Because S generates G. Therefore, this is the whole of G itself. In other words, this is true for every B in G. T inverse B belongs to F. In other words, T is measurable.
Yeah. Okay.
Is it okay?
Yeah.
That was the argument. Because of that, we don't have to do the complicated checking with sets which we don't understand and all that.
Yes. Okay. Thank you.
So there are so many complications in this course that whenever there is a simplification, you should feel happy. So many times my claims are that, okay, you can't do this, you cannot check like this. It's not enough that two measures are equal on a generating set so for them to be equal. So usually I bring you only bad news. Occasionally I bring you good news. Okay. So let's see another example. Say T from R to R. If T from R to R is continuous.
Sir, in the above example, yes, just the assumption of non-decreasing, from the assumption of non-decreasing, we can say that T is measurable, or we need some other conditions also, like finiteness and all those things are not. Oh no, sorry.
We can T from R to R.
Okay, sorry. I actually missed something. Yeah, sorry.
But your question is kind of You are foreshadowing something that will come, but okay, when it comes, we will say. So we will want.
Yes, actually, sir, like I was thinking about another thing that you told that F's are such that increasing right continuous and like
No,
some finite test condition also you told one day.
that was
Then
okay. So these things, an increasing function will have limits on the left and right. I am not saying anything about them. They can be finite, infinite, doesn't matter. I don't care. Okay.
okay.
So that's
Okay.
not, there is something else that what your question is. I mean, it will come in a moment. I'll tell you.
Okay. Yeah.
Everything is finite. Okay. Suppose if T from R to R is continuous, again we put the Boyle sigma algebra here and the Boyle sigma algebra here. Okay. So then it is measurable. Why is this?
Because any continuous map maps interval to interval.
Continuous function maps intervals to intervals.
I mean, inverse image of interval is interval.
Or
But no,
otherwise, any continuous.
that is not at all true. You know, I mean, you look at sin x. So what is sine inverse of 0 to infinity? If you look at the inverse image of 0 to infinity, that means you get where it is positive, right? So you get a union of these open intervals. These are where the function is strictly positive. So it's not true that inverse image of interval is interval.
So you can consider any open set in
Yeah.
in Y and continuous function inverse image of because f is continuous, inverse image will be the open set.
Right. Okay. So inverse image of open set. So one definition of continuity is inverse image of open set is open. So for just simplicity, let me just say that T less than T is open for all T in R. Hence, in B. Of course, any open set is in B. So for all such sets, T less than T belongs to F, belongs to B. I mean this sigma algebra for all T. Therefore, hence measurable. Okay, that's the reason. Yeah, so be careful about that sort of thing. It's not correct. I think you had the right idea in mind. You just have to look at inverse image of interval. It need not be interval, but if it's an open interval, then it will get an open set on the other side, which is fine with us. Okay, that is fine with us. So continuous functions are also measurable from R to R. Here, let me ask you a small question. So what happens if I increase the sigma algebra on this side? So we said Boyle sigma algebra, right? Suppose I increase this to Lebesgue sigma algebra. Will it remain measurable or will it could it fail?
Remain measurable because it's bigger.
It's only better for us. Okay. Suppose I don't give you this. If I give Lebesgue on this side, will it make it easier or harder? This time it is harder, right? You are asking for more. Is it true that T from R to R is continuous? Then it's measurable. From B to L. Not so clear, right? I mean, it's not obvious. I have not proved this because this collection, this is not a proof. This is not a proof because these things, minus infinity T, minus infinity, these generate the Boyle sigma algebra. They don't generate the Lebesgue sigma algebra. So this way of proof is not going to work. What if okay, so this is somewhat difficult. Boyle sigma algebra on this side, Lebesgue on this side. Let me make it easier for you by making Lebesgue on both sides. That only makes it better for you, right? So if you have a continuous function from R to R, is it measurable from Lebesgue sigma algebra to Lebesgue sigma algebra? It's actually an interesting question. The answer turns out to be no. Okay, one reason why you can take why it's better to stick to Boyle sigma algebra. So let me just write as a remark. Those who are, there's nothing difficult. I mean, it's not trivial. You'll have to think. It is not trivial at all. But it is not difficult if I tell you what the proof. But let me just tell you anyway as a fact. Those who are curious can look it up, and maybe we can discuss at some other time. If I put Lebesgue sigma algebra on that side, so there exists T continuous that is not measurable. If you take Lebesgue on both sides. So it's not, so it's actually even continuous functions can fail to be measurable here, which seems a bit strange. Okay, it's not, it's a, for those who like challenging things to think about, this is an excellent exercise. You will,
I mean, you have to manually construct this function like non-measurable and the left-hand side, right?
yes, yes. So just remember the limits of what you have. It is not a very bad function. It will be measurable from B to B. I mean, it's a continuous function. How bad can it be? It is a continuous function, but it is not measurable from L to L. Yeah, exactly. You can produce a function. So this is just for now. You just take this as a good reason why we should stick to Borel sigma algebra. Okay, whenever we talk of real numbers, we'll talk with Borel sigma algebra. That makes it easier for us. Okay, what else do I want to say? Real valued functions. So here I said composition, but for real valued functions, I can do a lot more things. So let me give some more. Let me give some properties. So consider. So yeah. So we will look at functions. So let Tn be functions from x f to real numbers with Borel sigma algebra. So n equals 1, 2, 3, and so on. So then if I take supremum Tn, infimum Tn, limsup Tn, liminf Tn, and limit, of course, if it exists. Are all measurable. One caveat, they have to be finite. Okay, so that let me say afterwards. Are all measurable. So let's put the caveat, provided they are finite. Otherwise, they are not functions from x to r, right? See, if supremum Tn can take the value plus infinity, then it's not a function from x to r. So by the way, what is this? This just means this is the map which takes, if this is t, t of x is supremum over n of Tn of x. That's, I'll just write this one thing explicitly. That's what it means, right? So that's what I mean. But it better take values in real numbers. If it's infinity, then it's not going to work. Okay, as written, it doesn't make sense. So that's why I say that provided they are finite. So that caveat I put.
Sir, shouldn't the hypothesis have Tn are measurable or something like that?
Yeah, thank you. So that's first and foremost very necessary. Thank you. Yeah. So yeah. So let Tn be x to r. Okay. Maybe all measure. Okay. So maybe assume be measurable. Okay. So start with measurable functions, countably many of them. Then you can into real numbers, then all these. Okay, I forgot. I can even add summation Tn. Or even you can put some coefficients. All measurable, provide again if this exists. Okay, again here also I should say if it exists. And is finite. That I have said below, so I don't need to write. If it summation convergence should hold. But when we say this series converges, we often allow plus infinity, minus infinity also as limits. In always when we take limits, lim sup, etc., we allow those plus infinity, minus infinity, right? So that's why I have making the caveat that provided these are finite, then they are all measurable. It makes it very convenient. By the way, this makes it almost difficult for you to produce a non-measurable function. Why? I mean, whatever you do operations, you are going to stay within the class of measurable functions. I mean, all sorts of countable operations. It's important that these are countable operations, not uncountable operations. Uncountable operations, no guarantee. Now, by the way, the last one in particular, just in case it is not clear, as corollary, I mean, it should be clear, but let's be very explicit. In particular, I just wrote it for countably, which of course also means for finite. Okay, in particular, sum of measurable functions is measurable. I mean, here I mean finite. The sum of two measurable functions is measurable, or max of actually that reminds me, I can also take product, which I did not write about. So maybe I just add that also here. If it exists. If it is finite, there is no problem. Yeah, if the infinite product exists, that means it converges. So you take partial sums and don't worry about that. So sum and product of two measurable functions are measurable. That's what I am saying here. Okay, so all these are true. Okay, sum, product, maximum, minimum, max or min. Of course, here I can also take min. There is no difference. My max or min. You can take a scalar linear I mean, instead of sum, I could say linear combination. Okay, linear combination of two measurable functions is measurable. Min, max, product, all these are measurable. Okay, even countable operations are fine, but there you have to put the caveat, you get something finite. If not, then it doesn't make sense. So this makes a lot of things. I mean, so pretty much it's hard to think of things which are not measurable, right? So yeah, so this gives you many examples. So let's see one or two proofs here. These are not difficult at all. So maybe I give proof of one or two of these and then leave the rest. Anyway, infimum. Okay, supreme. So let's say word about proofs. Any questions about these statements? This is all good news for you. Okay, so lots of things you do will remain measurable. Remember, you should do countable operations. That's the only thing you should remember. Okay, so let's say T equals sup over n Tn. Okay, so then assume finite. Then T is a mapping from X to R. And if I look at T less than T, okay, so what does this mean? T less than equal to T. What does T less than equal to T mean? Supremum is less than equal to T. It's same as, so remember that this is all those X such that T of X is less than equal to T. So what should happen if T of X has to be less than equal to T? Every one of these has to be less than equal to T. So this is just the intersection over n, Tn less than equal to T. See, Tx less than equal to T if and only if Tnx less than equal to T for all T. So as a countable intersection of each of this is in measure is F. Hence the countable operation is in is okay. So this is very simple. So supremum is measurable. Similarly, infimum, or you can just do infimum. You write as supremum of negative of the supremum of negative supremum. Okay, so that finishes this one. So I proved this one.
Sir, all of this true for Boole sigma algebra, right?
Yes, always on the right side we are putting the Boole sigma algebra. Yes. So it is on the right side, it's always, so here it is F, here it is B. On the target, when the target is real numbers, it's Boole sigma algebra. No questions. Right? So that's why, that is one of the points I made here, that things go wrong when you put Lebesgue. So we'll always, on the target space, always, if target space is real numbers, it's always Boole sigma algebra. That's why, because Boole sigma algebra is generated by these things. If it was Lebesgue, you would not be able to check it by just checking these generating sets. I mean, these are not generating for the Lebesgue sigma algebra. Any other questions? Okay, so let's see how do you do it for. Let's do it for T equal to T1 plus T2. Just sum of two functions. Let us look at that. How can you do this? Assume, so both are finite. I don't have to assume anything is finite. So T is a mapping from X to R. So how do I write T less than equal to T? How do I check that it is measurable? I know T1 and T2 are measurable.
Intersection of Tn less than equal to T by 2?
There is no T, only two, T1 and T2 are the only things. So can you say again?
Intersection of?
Okay. How many things?
Intersection of I equal to 1 to 2. Ti is less than equal to T by 2.
1 second. So I'll just write it as intersection of two things. So you want to write it as T1 less than equal to T by 2 intersection T2 less than equal to T by 2. Is this true?
Not necessarily, right?
That's not
No.
necessarily true. One way is correct. One way is correct, but the other way is certainly not true, right? I mean, why does, if the sum has to be less than equal to 5, it's not necessarily both of them have to be smaller than 5 by 2, right? So this is only true. This is a subset of this. That's not. So what do you do?
Can we do something, along similar lines? Say T1 is less than equal to K, and then your T2 will have to be correspondingly a different value, less than equal to, say, T minus K.
Okay. So
And then you take the union over all of those Ks.
1 second. So you want to, let me not use K, as K I keep for integers. So you want to write like this, sum S, and this is less than equal to
T minus S. Essentially, this is what we do a lot of times in probability theory.
But what is S?
A union
them to be
over all
rationals.
possible values.
Over union over.
Rationals mean.
Will rationals be enough though?
Yeah, let's come to that 1 second. So let me write what you said first. So it's the union over all S. For the moment S in R, first, let's say. This is actually correct, right? Is this correct? I mean, suppose the sum of two numbers is less than equal to T. Let the first number will be some S and the second number has to be less than equal to T minus that S. So this is actually true. So there is no problem about this. This is actually correct. Okay. Problem is this does not help you to conclude because this is an uncountable operation. Can I do with rationals?
Yeah, I think S belongs to Q will be here. Then, like as a set Q is.
So this is true, but uncountable operation. That's the point. How to conclude? Okay. So now let's try the next thing. Is it true that it is S in Q? Is it true?
This itself is probably not true, like this equality.
Why? Can you give an example?
I mean, there are probably three irrationals A, B, C such that A plus B equals C.
Right. Yeah. You are right. Exactly. So you can take. So for example, if what is it? 1 second. So why is this not true?
You can take pi and 2 pi.
Yeah. So root 2 and 2, right? That's will do. Okay. So if T is, let's say, 2 square root of 2 or something, so then or rather 1 second. So what I mean is if T1x is root 2 and T2x is also square root of 2, let's say, then T of x is 2 times square root of 2, right? That's the sum. So x does belong to T less than equal to 2 square root 2. But x does not belong to the right hand side. Because you are not allowed to take, I mean, how will you split it? If you take S to be, if X has to belong to this intersection, if X has to belong to this one, if X has to belong to T1 less than equal to S, then S you have to take strictly larger than square root 2 because S is rational. So S has to be larger than square root 2. But then T minus S, namely this T is 2 minus S will be smaller than square root of 2. So this doesn't work. So this equality is false. So what do you do?
So how about this? We allow for a epsilon error and we take an intersection over a lot of these rational epsilons.
Okay, so good. So but is it clear to everyone that this does not work? So that explains what we do next. See, there is no limit to how many countable operations you do. Okay, so this doesn't work. Okay, third attempt. So what we do is, what about T less than T? If I just take T less than T, can I do S in Q, T1 less than S? Is this correct?
I think this is correct.
This one is correct. Okay. So there it makes a difference whether you put less than equal to or that. I mean, just for the writing purpose. Okay. So what you can do is what Shekhar said also, but This may just slightly simplify your task. If this cycline is true, okay, so check. I will leave it for you to check. Once you check this, then you are through, because this is where you should leave yourself the flexibility of using any of these sets. Sometimes open and sometimes closed are convenient, so you just leave yourself the flexibility. This is okay. If this is true, then it is a countable union also. And this belongs to F, this belongs to F. So countable union of intersections of elements in F. So this belongs to F. So T, sum of two measurable functions is measurable. Is it okay? So let me do one more so that you can participate in and tell me how you will do this. Any questions about this sum, by the way? So all this doesn't work. So the whole point is this all was something that they are correct in the right direction, but I think that was not the complete solution. The complete solution is here. Any questions? Okay. What about t equal to? Do you like lim sup or limit?
Limits, sir, please, limits.
Limit. Okay. You should get used to lim sup limit. They are nice. They're very convenient. Okay, let's try assuming it exists. And is finite. Pointwise. Meaning for each x, Tn of x has a limit, and that is T of x. That's what it is. And Tn are measurable. So how do you show T is measurable?
So maybe we can write T as T minus Tn plus Tn, and then
Right.
do a limiting argument, take an epsilon and stuff.
But no, but still you have to show T minus Tn plus Tn. Tn is measurable, but T minus Tn may not be measurable, right?
Yes, but T minus Tn kind of goes to 0, right? So
Yes.
it should have a negligible effect.
It's going to 0, but why is it measurable? Ultimately, you have to deal with something like this, right? So you have to look at maybe T. So can you write it as in terms of this? So we assume that the limit exists. Don't worry about the existence of the limit at the moment. Okay. Let's assume the limit exists. So then how do you ensure that the limit is less than equal to t? Or if you prefer, you take t less than t, whichever. Last time we saw one is more convenient than the other. Can we write it in terms of tn's? So for example, the first attempt would be something like silly and naive like this. This is not necessary, right? Is it true? This was true for supremum, not for limit. Why is it not true for limit? Well, first few tn's, nobody cares what happens to them. If t is less than equal to 0, doesn't mean t1 has to be less than equal to 0. First 100 of them could be 5. So we do not have to have this. This is not necessary. So can you modify it?
You should have another limit before that.
Huh?
Limit m tending to infinity, and the intersection has to go from n equals m to infinity.
So you don't take the intersection here. Yes, so let's give ourselves a bit of space. So we want to take the intersection over n equals, say, k to infinity, Tn less than equal to t, and then
Take the limit as k goes to infinity.
by limit, okay, what happens as k, this is an intersection. When k increases, this is a smaller intersection, so it becomes larger. So by limit, you mean just this. It's limit of sets, right? Increasing sets. If you
Correct.
make k
Yes.
larger, it becomes larger. So what you are suggesting is this. Is this true? If t of x is less than equal to 0, is it true that, I mean, is it the same as this?
No, right? Because we could have TNX oscillating, right, around T.
Oscillating. So it's the problem.
I think if you take the strict inequality in the left side, that will do it.
Sorry?
Strict inequality in the left side.
So the problem is, for example, this doesn't.
Because the limit can approach from the right side from t, right?
Exactly. So you could have Tnx to be 1 by n and Tx to be 0. So, and if t equal to 0, if I put 0 here, then Tx is less than equal to 0 is correct, but at no time is Tnx less than equal to 0. Okay, so that is, again, you can give yourself an epsilon and adjust that. So what you can do is well, if you want to adjust it here, I will leave it as exercise, but okay, let's go to the other side. So what you're suggesting is maybe this is this true? Less than t, is that right? Is this true?
No.
This is also not true. Why?
So Tn could be oscillating around T, right?
Yeah, it could be oscillating around t,
Convergence is the issue, right?
but it is
Yeah.
less than, right? Strictly less than, so it can't go beyond t.
Okay.
But the problem is, so what is if Tnx is minus 1 by n, Tx is 0. Now, if I take 0 here, x belongs to this, right? Because Tnx is in minus 1 by n, so it belongs to all these things. But it does not belong here, because here I have strict inequality. So this also fails. So this is also not true. So what do you do? Well,
Maybe we can try Tn less or equal to T minus epsilon.
say it again.
No, I'm also thinking out loud, sorry.
No, you are right actually. So what you should do here is, so this side, which way was the inequality going? I mean here, if all this holds, then this is true, right? The other way is not true. Is that what happened? Okay, so we can adjust this actually. So what we can do is okay, so let's see which way it goes. So let us say this is this. Yeah, if this is true, what is it I want to say? So let us say, so if Tn is right here, it could become equal to T. That is our problem, right? Here it could become equal to T. So let's take T minus 1 over m. Suppose, don't worry about the left hand side. So look at the right hand side. So this allows both the limit to be less than T minus 1 by m, but also equal to T minus 1 by m. That also is allowed. So you take union over m equals 1 through infinity. Something like this. So here also you can probably adjust by adding plus 1 by m or something like that. Okay. Check this. I think this part I can see. So this is measurable. Because each of these is measurable, and we are only doing countable unions, intersection. So, is this clear?
So you put union, shouldn't it be intersection?
Sorry?
You put union over m's.
Oh, this is intersection, is it?
I
No, I think it is union over m only. It need not be true for every m.
Right, it may not be true.
So it is, I think this is the union. Okay, check these things. Okay, so check. You can correct it if it is wrong. Something simple like this can be done. So you can check that limit exists. Okay. So it would be, I mean, so Shekhar was reluctant to consider lim sup, but life is always easier with lim sup and limits if you take it, because it goes one way bound. Anyway, so you do it also for lim sup and limits. Okay, so I think we have done enough examples. So 3 of them I have done. So now supremum I considered. Infimum is just from supremum you can get, or repeat. Limit we considered, and lim sup lim inf are similar. Okay, so this is similar to that. You can do them directly. Now this one we already did the finite sum. Finite sum is okay. Okay, we didn't do linear combination, but we did finite sum, and it's the limit of finite sums. So this is limit of finite sums. Limit of finite sums. Therefore, first finite sums are measurable, then limits of finite sums are measurable. Okay, only thing I didn't do is I didn't do linear combination, but okay, if t is measurable, 2 times t is measurable, I leave that to you. Okay. So this completes the proof here. So kind of went over it slowly, but it's okay. So you should get used to these things. Any questions so far? So measurable functions especially into real numbers are very important, and they are closed under all sorts of operations. So there is all sorts of things. So I will leave now as exercise a couple of things. It will be hard for you to find a non-measurable function. So exercise, let's give as exercise. So suppose I take t from R to R. Now let's take R to R with Boyle sigma algebra. I said if t is, so now show that t is measurable. If it is, let's say, left continuous. I showed if it is continuous, then it is measurable. But suppose it's only left continuous or right continuous, or if you know what it is, upper semi-continuous. Of course, lower. If you don't know what upper semi-continuous, lower semi-continuous are, you may ignore it, or you just look up the definition and then do it. I mean, if you just read the definition, and then you will be able to do the exercise. So it's kind of, so anything that's piecewise continuous is piecewise continuous means you can break your real line into intervals so that it is continuous on each of them. Then it's okay. So let me give okay, one thing I didn't say, I could have put it right in the beginning. Okay, let's do it here. So suppose I have xf to R, always with Boyle sigma algebra. So So let A be a subset of X. Okay. Indicator A from X to R. This is the indicator is defined as indicator A of X is 1 if X belongs to A, 0 if X does not belong to A. This is called the, I will always say indicator of A, of the set A. There are some books which use characteristic function of the set A. I don't want to use that because characteristic function is an overused thing. So I will always say indicator function. Okay. So then the claim is indicator is measurable if and only if A is itself measurable. A belongs to sigma algebra F. Okay, that's the claim. I hope the definition of indicator is clear. You use it in many parts of math, so you must have seen. So it is just 1 here, 0 here. Okay, so indicator is measurable if and only if A belongs to F. Why is that? So you just look at indicator A less than equal to T. So what is this? This is the set of X for which indicator is less than equal to T, right? So it is empty set. If T is less than 0, this is empty set because no X is there for which indicator A is less than T, less than equal to T, if T is negative. But if T is between 0 and 1, then what is this set? What is the set where indicator A is less than equal to T, for T between 0 and 1?
A complement.
It is A complement because that's where indicator A is 0. On A, it is 1. On A complement, it is 0. If T is strictly less than 1, then and greater than equal to 0, you get A complement. Here, less than equal to T, if it is indicator is always less than equal to 1. So this will be the whole space. So the only question is which one is measurable. So this is, so A complement has to be measurable. Because this one is anyway in F, this one is anyway in F, we don't need to check. It is only this intermediate thing, which is same as A belongs to. Okay. So this way, what is the point of this? Indicator functions of measurable sets are measurable. So measurable functions, so measurable sets A in F can be identified special case of measurable functions. By identifying A on one side with indicator A on the other side. If you see A and indicator A have the same information. A is a set, indicator is A is a function which puts 1 here and 0 there. So they have basically the same information. So the point is that, so that way if I identify a set with its indicator function, then sets become special case of measurable sets become special case of measurable functions. Other way to think of measurable sets is sets are yes/no type questions. Functions can take many different values. They are more subtle measurements. So you can measure a person's height, right? You can measure a person's height, and that is a number. But some other things, whether the person is male or female, is if those are the only two options, then they are that's an indicator function. So that's just a two-variable thing. But so in that sense, indicator functions are special case of measurable functions. But one of the things that will be a running theme is you can also go the other way. you can approach functions using sets. How is that possible? Functions are more general measurements. How can I approach height, for example, by asking yes-no questions? So if you have played things like 20 questions, there is this game of 20 questions, you know, anything can be converted into yes-no questions. Not one question, but several yes-no questions. So if you want to know somebody's height, you can ask, is the height less than 160 centimeters? And depending on the answer, then you can ask, if the answer is yes, then you ask, is the height more than 150 centimeters? And by doing this questioning, you can arrive at the number. So this is a way of working which will be repeated many times. Okay, so just a remark. Elementary, but this is a remark. Okay, any questions so far? Okay, so I have a few minutes, so let me do one thing. So by and large, we are going to stick to measurable, real valued measurable functions. That's what we will integrate. But here, let me do one thing that I started out with, which I did not finish, called the push forward of measures. Well, I kind of did it in a hurry that day, push forward of a measure. So X, F, mu is a measure space. Okay, so this is a measure space, and Y, G is a measurable space. So I don't have a measure here. And let us take a function t from X to Y. Assume t is measurable. Then define mu of B. So for B in G, I define mu of B as mu of the inverse image of B under T. Okay, so I pull back, B is here, B is a subset of Y, I pull it back to a subset of X. Because T is measurable, if B is in G, that pullback set will be in F. So I can apply mu to that. So it makes sense because I cannot talk of mu of something that's not in F, but this is in F. So claim is then mu is a measure. On Y, G. Okay. It is denoted, often we write mu T inverse. Just again, T inverse is not a function, but it is very easy, convenient to remember. You know, mu T inverse, that's all it is. Mu of B is mu T inverse of B. Okay, formally it is a very nice way to write it, mu T inverse. Just apply that. And call the push forward of mu under T. So why is this a measure? So this is more or less straightforward actually. So the proof if Bn and G are disjoint, then T inverse Bn belong to F because T is measurable are also pairwise disjoint. Because if X belongs to T inverse Bn, that means T of X belongs to Bn. Now Bn's are disjoint, so Tx can belong to at most one of the Bn's. So you can't have an intersection. If x belongs to T inverse B1 and T inverse B2, then Tx will have to belong to B1 and B2. But B1 and B2 are disjoint. So these are also pairwise disjoint. Hence, mu of union of T inverse Bn is actually sum of mu of T inverse Bn, and by definition that is nu of Bn. And by definition this is mu of this is mu of but one thing. Okay, so this is the union is fine, but that is also the same as we saw T inverse of the union of wheels. We saw inverse image behaves well like this, but that is just mu of union wheel. Okay, so nu of union Bn is nu of summation Bn, hence nu is a measure. Okay. So this way we can get push forward. If you have one measure, you can push it forward to other measures. So one example here is, so I'll just finish with these examples. Any questions about this push forward concept? So you can get new measures from old by just pushing it forward under measurable functions. That's all. So example. So let F.
It's 5 o'clock.
I will take a minute or two if it is okay. Let F from R to R be a CDF. Okay. So which means it is non-decreasing. Right continuous. And it has this limit behavior. Fx goes to 0 as x goes to minus infinity, and it goes to something finite. As x goes to plus infinity. Let's take like this. Okay. So this is a function which looks like this. It could have jumps. So for simplicity, let's take no simplicity. Let's just define it straight. Define T from, so let us call this number B. Let's call this number B. So I define T from 0B to real numbers. So F maps real numbers into 0B. T will be basically the inverse of that. It's increasing almost like that, except you have to be a little careful. You define it as infimum of all x such that Fx is greater than equal to U. Let's see. Yeah. So let's take this. Tu is the infimum. So if F is continuous, the only case you should think of really strictly increasing. Don't worry about jumps and all that at first. Imagine that it is F is strictly increasing and continuous. Then T is just the inverse of F. So then T is non-decreasing, hence measurable. So what I'll put down the claim, yeah, so maybe I will justify it next time. So if you take, let lambda be lambda Lebesgue measure restricted to COB. We know the Lebesgue measure restricted to this. And I define mu to be lambda B composed T inverse. That is, it is the push forward. Push forward of lambda B under this mapping T. So claim is that mu is the measure with the CDF. That's the measure with CDF. So last time we have earlier said that given any CDF, there exists a measure with that CDF. One way to construct it is instead of going through all the category business, here is the explicit way of doing it. I have given you a straight mapping from some interval to the real line, and I'm saying that you take Lebesgue measure on that interval and push it forward under this mapping, you will get the measure whose CDF is F. Okay, I will explain this maybe next time. Sorry, I'm over time. I'll stop. If there are any questions, so class is over. I will explain that next time so people can ask questions if any. If not,